Everyone thinks baking is just following a recipe. They're wrong. Baking bread, at its heart, is a masterful dance of physics and chemistry, transforming simple ingredients into something truly magical. We often measure, mix, and knead, then let the oven work its quiet wonder. But what truly happens inside that dough as the temperature climbs? It's a process far more intricate than just cooking. It's an engineered transformation, a symphony of molecular changes, each dictated by the precise application of heat. From the moment that dough hits the warm air of the oven, a series of invisible reactions begin, meticulously building the structure and flavor we crave. Our journey begins with water, that unassuming liquid. In the initial stages of baking, around 100 degrees F, 38 degrees C, the water in the dough starts to warm up, activating our microscopic heroes, the yeast. These single-celled organisms, dormant until now, spring to life, feasting on the sugars in the flour. As they consume sugar, yeast produce carbon dioxide gas and alcohol. This gas, trapped within the elastic network of gluten, is what makes the dough rise, creating those airy pockets. Think of it as a tiny biological gas factory, silently puffing up your future loaf. But the yeast's reign is fleeting. As the oven temperature climbs past 140 degrees F, 60 degrees C, their activity slows dramatically. By 160 degrees F, 71 degrees C, the yeast cells are effectively deactivated, their work done. This delicate balance of yeast activity and heat is crucial for proper leavening. Next, let's talk about gluten, the unsung architect of bread's structure. Gluten is a protein network formed when water interacts with flour, specifically the proteins glutenin and gliadin. Kneading helps these proteins link up, creating a strong, elastic web. This gluten network is like a microscopic balloon, able to trap the carbon dioxide gas produced by the yeast. Without this elasticity, the gas would simply escape, leaving you with a flat, dense disk instead of a fluffy loaf. It's the framework that holds the entire structure together. As the temperature in the oven continues to rise, reaching around 160-180 degrees F, 71-82 degrees C, a crucial process called protein denaturation begins. The gluten proteins, having stretched and expanded, start to set. They coagulate, much like an egg white firms up when cooked. This setting of the gluten is what gives bread its final, stable structure. It's the moment the balloon hardens into place, creating the crumb and holding those gas pockets open. Without this, your bread would collapse as soon as it left the oven, a disappointing deflated mass. But gluten isn't the only component undergoing a transformation. Starch, the main carbohydrate in flour, also plays a vital role. Around 140-160 degrees F, 60-71 degrees C, starch granules begin to absorb water and swell, a process known as gelatinization. This gelatinization contributes to the bread's soft, moist texture. The swollen starch granules fill in the spaces within the gluten network, preventing the bread from becoming too dry or crumbly. It's like the mortar between the bricks of the gluten structure. As the temperature climbs even higher, above 200 degrees F, 93 degrees C, the remaining water in the dough begins to evaporate, turning into steam. This steam, trapped initially, helps to further expand the loaf, contributing to the oven spring, that final burst of rising in the first minutes of baking. This steam also helps to keep the crust soft for a crucial period, allowing the loaf to expand fully before the crust sets. Imagine a delicate, invisible pillow of moisture protecting the expanding dough, giving it just enough time to reach its full potential. The final act, and perhaps the most visually satisfying, is the browning of the crust. This occurs at temperatures above 300 degrees F, 150 degrees C, and involves two distinct chemical reactions, caramelization and the Maillard reaction. Caramelization is the browning of sugars, giving the crust a sweet, nutty flavor. Think of what happens when you melt sugar in a pan: that rich, amber color and complex taste. The sugars on the surface of the bread undergo a similar transformation. The Maillard reaction, however, is far more complex and responsible for most of the deep, savory flavors and aromas of baked goods. It's a reaction between amino acids and reducing sugars, creating hundreds of new flavor compounds. This reaction is why a golden brown crust tastes so much more complex and satisfying than a pale, unbaked one. It's the same reaction responsible for the delicious smell of roasting coffee or searing steak. It's a symphony of flavor creation, right on the surface of your loaf. The crispness of the crust is also a result of the heat. As the surface of the bread dries out and the sugars caramelize, it forms a hard, brittle layer. This textural contrast between the crunchy crust and the soft interior is one of the hallmarks of a truly great loaf. And what about the internal temperature? For most breads, a finished internal temperature of around 200-210 degrees F, 93-99 degrees C, is ideal. At this point, the starches have fully gelatinized, the gluten has set, and enough moisture has evaporated for the crumb to be firm yet tender. Removing the bread from the oven doesn't end the process. As it cools, residual heat continues to cook the interior slightly, and the moisture redistributes. This is why patiently waiting for your bread to cool before slicing is so important. Slice too soon and the crumb can be gummy or dense, as the starches haven't had a chance to fully set. The structure is still a little delicate, still undergoing its final, subtle transformation. Patience is truly a virtue in baking, guided by these invisible physical laws. So the next time you pull a warm, fragrant loaf from the oven, take a moment to appreciate the silent, intricate physics at play. From the yeast's humble beginnings to the golden crust's complex flavors, every step is a testament to the power of heat. It's not just an ingredient, it's the catalyst, the driving force that transforms simple flour and water into the comforting, universally beloved food we call bread. A true everyday miracle, orchestrated by the fundamental forces of our world. What other everyday transformations do you wonder about? Let me know in the comments below. What other everyday transformations do you wonder about? Let me know in the comments below.